Hi, in this lecture I'll be covering the four main mathematical objects usually encountered when doing linear algebra or machine learning stuff. This should be mainly review, except for maybe the last one with tensors. Yeah, so this should be review. But I encourage you, even if you're very familiar with these things, to just follow through this, or maybe watch till the end, just to get an idea of what's the notation that we're going to be using in this course, because it might be different than something that you've used in the past. Just one more note, this goes with chapter 2.1 of the deep learning textbook that this course accompanies, so I highly encourage you to read that after watching this lecture. Alright, so let's start from the top and then go to the bottom. So we'll start with scalars, which is the easiest. So scalars is any single number, so 3 or negative pi or anything like that. 2 billion, cajillion, willion, doesn't matter, it just has to be one single number. And the only thing to remember this is when we're creating variables that are scalars, we represent them with a lowercase letter that's not bolded, so unbolded lowercase letter. And we always want to declare what set of numbers this variable comes from. So for example, if we're saying something like this, which is usually the most common, we're saying that x is an element of the set of real numbers. So that means x can be any number that's in the set of real numbers. And the real number set, just for review, is basically any number that can be, if you imagine a number line going from negative infinity to positive infinity, any number along that line will be a real number. Okay, so we got that. So just, this can be also, x is an element of any other kind of popular set of numbers. So this is another one, natural numbers. So that's like counting numbers. It's like 1, 2, 3, 4, 5, or maybe often seen as this one as well. So integers, so x can be any integer, stuff like that. So kind of a natural extension of this into the next dimension in a way is vectors. So vectors are basically just ordered lists of numbers. So maybe an example would be 2, 3, 5. So this is a three-dimensional vector, we'll say. We call it a three-dimensional vector because another very popular way of interpreting vectors are points in space. So just maybe a very quick review on that. If we have some two-dimensional vector, so something like this, and maybe we say this is 2, 1, then we can represent this as a point on the Cartesian coordinate plane at x equals 2. So let's say this is 1, 2, 3, 1, 2, 3. So we can represent this as a place in the Cartesian coordinate plane at like here. So 2, 1. So this is 2, 1. It's kind of messy, but I think you get the point. So often a very popular way of kind of understanding vectors is as kind of marking off some point in a coordinate space. So when we have a three-dimensional thing, you can imagine it in 3 dimensions as pointing out some place which is an x equals 2, y equals 3, and z equals 5. So some point, I don't know, here or something like that. So that's just a popular way of kind of saying that. So that's kind of often why we say these things, when we call these things three-dimensional vectors or two-dimensional vectors. And kind of the general extension of this is some vector which is like this. We'll say this vector x, and I'll get to that in a second. Some vector x has some x1, x2, into xn. We call this an n-dimensional vector. So you can imagine this as kind of describing some point in n-dimensional space. And one more thing, how would you kind of differentiate this x from a scalar x? Well, the thing is, when you're dealing with vectors, you're also having lowercase variables, but they're going to be bolded. So whenever you see a bolded lowercase variable, then it's a vector. It's kind of hard to do bold sometimes when you're drawing on Blackboard or when you're going on paper. It's easy in text, but often you'll encounter something like this with an arrow on it, and that also means it's a vector. Okay, so a few more things just with these. Similar to these, you do have to declare what set all of these numbers can come from. So if you're saying that all the x1, x2 up to xn, they all come from the real number set, you would say bold x comes from the real number, and then you'd put it to the power of how many elements you have in that set. The origin of this notation is a tiny bit complicated, but I'll see if I can very quickly cover it because it's quickly mentioned in the text and it's nice to understand. So in the text it says this comes from a Cartesian product of basically of real numbered sets. So what that means is something that you might have encountered before is a Cartesian product. If you haven't, that's okay. So a Cartesian product is basically just some element, it's an operation you can do between two sets. So say we have two sets that have the same amount of characters in them. So let's say, and a set is just a set of numbers. It's a collection of numbers. So let's say we have a set which is A, B, and C. So this set has A, B, and C. And then we have a second set which has, let's say, D, E, and F. D, E, and F. So we have two sets here, right? Two sets. And basically taking the Cartesian product of these two sets is to create all possible ordered pairs that take one element from one set and one element from the other set. So we can kind of quickly draw these, all these possible ordered pairs that we can get from this. So we can pair this A with this D, we get A, D. We can pair this A with this E, and we get A, E. Likewise, A, F, and then B, D, B, E, B, F. And then we can do, C, D, C, E, and C, F. So you can see that if both of our starting elements are both of our starting sets have 3 elements each, then our resulting kind of Cartesian product of them, which will show all the possible different ordered pairs that we can get from getting 1 from each, is going to be 9, which you'll notice is 3 squared. So if we have 2 sets that each have n elements in them, we're generally going to get an n squared kind of ordered pair if we're getting 2 of these sets. But if you imagine getting 3 possible sets and doing all the ordered pairs, or all ordered triplets from all 3 of those, you'd get something which is n3, and that's why we kind of generally say that instead of our set being just 3 numbers, A, B, and C, our set is just all possible real numbers. And then we kind of say this Cartesian product of taking n possible ones is taking n. So we're saying we're kind of taking the Cartesian product of each of these sets, and then resulting is just this single set. Another way to maybe interpret this is that just starting with a single scalar, there's think of every possible number in the real numbers, which is infinite. So if you have one scalar, so if you're saying x1 is an element of the real numbers, and then you're saying x2 is an element of the real numbers as well, that means theoretically if you have a vector that's x1 and x2, that means there's kind of R2 possible, possible version of this, if you think. If we have x1, there's this many kind of possible versions of this x1, but now that we have 2, now those possibilities have kind of squared, if you can understand it like that as well. Those are kind of just 2 popular ways to understand where that number comes from. Generally, just the one thing you have to remember is when we're dealing with some sort of vector of n dimensions, n elements, we represent it as that. And yes. One more thing, if we want to index vectors, which is a popular thing to do, so if we have some, let's take the same example here, if we have some n-dimensional vector and we want, say, we want the 4th element in there, so we want the, the 4th element, wherever that is in between here, we would just say x4. So if we were talking about the 4th index element of that. And generally, obviously, just from the ith element, you get some xi. As well as that, if you want to index several things at a time, so if you wanted 1, 3, and 5, so if you wanted the 1st, 3rd, and 5th elements of this vector, you kind of have to do something that's a bit cumbersome, and luckily we don't really do it that much. But say, again, if you wanted the 1st, 3rd, and 5th elements of this, you would have to make another set, S equals 1, 3, and 5, and then you'd have to index this vector x to that set. So that would be xs would basically be equal to x1, x3, and x5, which I think makes sense, but it's a bit cumbersome. And just the last thing, and kind of a shortcut in indexing as well, say if we want to index every single number except for the 1st, 3rd, and 5th elements in this, we would take the complement of the set, which is basically putting a negative sign. So basically, while s is 1, 3, and 5, this negative is every number that's except for 1, 3, and 5. So we would just index to the complement of that set, and that would be equal to every number, so x2, x4, x6, onto xn. And the last thing like that, you can also take the complement of a single number. So if you want every single thing in this vector except for the 1st element, you would just say x -1. Okay, hopefully that clears it up, and that's kind of the longest one to talk about, but they're also the most used of these, possibly maybe tied with matrices and machine learning, but vectors are very often used, so it's good to get those down solidly. The last, well, tensors and matrices are pretty similar in this context, but matrices is kind of the last big one we want to talk about, and matrices, I'm just saying, there's my eraser. Matrices are basically just increasing this to a two-dimensional thing. So we're getting one extra dimension on here. And what I mean by that is now we're just getting a box of numbers. So, you know, just to say, then we have some A11, A12, A13, A21, A22, A23. I'm just going to index all these for good measure. And I'll explain how this indexing works in a second. But this is, we call this a 3 by 3 matrix. As you notice, we also can call this a square matrix of numbers because the amount of columns is the same as the amount of rows. And basically this is just increasing the vector to kind of more numbers in a way. The way we represent these is usually with a capital letter. That's usually bolded, so bolded capital letters. So often the default, the default with scalars is often X. With matrices, it's often A. So you represent this with some A, some capital A. So this vector is A, and then we can index each of these first with the row number and then the column number. So if we wanted something in the first row and the third column, that would be first row, third column here. So it'd say A, first column, first row, third column. So that's kind of how you index them. And if you want to declare it, similar kind of theme to the scalars and the vectors, we have to declare what set our variable is coming from. So let's say every element in this is coming from the real number. So each of these A11, A12, blah, 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 is all from the real number set. We would say, predictably, that's like this. But now the only thing different is instead of having Rn, then we would have Rm by n, where m is the amount of rows and n is the amount of columns. So that's just one thing to mention there. And of course, as similar to those, we can have the integers here or the natural numbers here, whatever you want. And yeah, so these are often seen in machine learning just because vectors aren't often enough to hold the data that we're dealing with. And yeah, so these are matrices. So the last thing, and I'm just kind of thinking here, is there anything that I'm missing with that? I don't believe so. Oh yeah, yeah, so you index them like that. You might also see it indexed like this as well. You know, there might be a comma between them and it might not be, and that can get a little confusing sometimes if you're getting huge vectors, but then you might have something like A11034, and you know which ones are the columns, which ones are the rows. You kind of have to take from context clues, but usually we are nice and kind of put commas on them. Okay, one last thing is tensors. So tensors are basically just kind of increasing this into more dimensions. So if you can imagine a tensor, and we often deal with tensors again in machine learning just because we need a lot of room to store data points. You can imagine as kind of making this a 3D kind of cube of numbers in a way, where we have each of these represented with one number representing the first kind of layer. So say if we have 3 kind of layers here, you can just think of it as stacking 3 matrices on top of each other, and we would index something in this kind of cube, so with 3 numbers now. So if something in the first matrix, I guess, first matrix, first row, first column would be 1, 1, 1, so that'd be like this element here. But if we want to index something maybe here, so maybe that's the third matrix back, and then we want the something like here but back, so we want that to be the first row and the third column. So that would be the element here. So it kind of gets hard to think about, but you can end up just kind of not thinking about it too much if you can kind of get what I'm talking about. You can just index it with 3 letters, and just a way for us to kind of put more data in one thing. So you can think of it just as a kind of a 3D'ing of the vector, of the matrix, sorry, and you can access them like that. And similarly, you declare them also with a uppercase variable, but it's kind of obvious that it's a tensor just because when we're declaring what set all these numbers come from, so usually the real numbers, we have to do some m times n by j or k, which basically says it's this many rows, this many columns, and j is how kind of deep it is, if you can get that. Okay, so that's all the main kind of data structures or mathematical objects that we're going to be dealing with in linear algebra. Hopefully that makes sense. And yeah, so our next video is going to be doing some operations on matrices specifically, but also some stuff with vectors. So I'll see you there. Bye.